Hey guys, this is Notes video 12.7. This is going to be our last video on acids and bases. We're going to be talking about titrations today. You guys are going to be performing one of these. My hope is that you have watched this video before we do that titrations lab, which will be this week. So try to get through this at least. But really, these are very important. This is a process that is done regularly and routinely throughout labs all over the world, because titrations are used to calculate the concentration, which again, concentration, we're using molarity, right? Moles over liters, of an unknown solution. Okay, so we have an unknown solution. We want to figure out the strength of it, and we can do that based on stoichiometry between the molarity or the moles of acid versus the moles of base and how much that it takes to neutralize it. So acid of an unknown molarity is reacted with a carefully measured amount of a base of known molarity to the point of what's called neutralization, which we learned about in our last video, right? So think back, what does neutralization mean in terms of ions? All right, it's where the hydrogen ion concentration equals the hydroxide ion concentration. Or we can do the vice versa of that, where we could take an unknown molarity of a base and then react it with a carefully measured amount of known molarity of an acid, and then we can still do the same neutralization reaction. In all neutralization reactions, guys, there has to be a 1-to-1 ratio. Oops, that is not how you do that. All right, between moles of H plus and the moles of OH minus. So in our class here, that is going to be true to where, I still didn't even write it right, 1-to-1 ratio. But you can have, diprotic and triprotic acids or bases, or dihydroxy or trihydroxy bases, and still use those. But we're not going to have to worry about it in this class. Ours are going to be 1-to-1. If it has a diprotic or triprotic or whatever, you would just have to make sure you account for that third or second hydrogen in your calculations, okay? So in a titration, when you have those concentrations equal each other, that means specifically that you have the moles of H plus ions equal the moles of OH ions, okay? So if we're thinking about a picture here, okay, here's my beaker. Okay, I've got all these, let's say, H plus, okay, my unknown acid in here. I've got all these H plus ions floating around in there. And then I'm going to take hydroxide drops, and I'm going to drop them in there. So this is hydroxide, right? So that each drop is going to effectively neutralize one of the hydrogen ions. So they're going to neutralize each other. When you get to the point where, let's say, okay, now this guy has an OH minus, this guy has an OH minus, and so on, where all of those ions in solution have been neutralized, okay, that's where we have what's called the equivalence point. So in a titration, and I'm going to show you the setup here in just a minute, you keep adding drops until they equal each other. Okay, and then that's when the titration's complete. So when one of the things you got to think about is, well, what indicator do I need to use that will allow me to see that pH change, where strong acid, strong base type piece, okay? So titration's complete when we're at that equivalence point. The end point, however, all right, of a titration is the pH of the solution at the desired color change. Okay, so let's say if I'm using something like, let's say for example, phenolphthalein, okay, it's got an indicator range change of 8 to 9. So its end point would be 9, where it's that pink color or somewhere in between that. Well, if we were doing, a strong acid with a strong base, we want it to have a pH of 7. So our equivalence point is actually going to be before that color change. And this is something to think about for your lab that you're going to be doing. You don't want to see that pink color. You want it to be as faint as possible, because if you've gotten to where you actually see a pink, that means you've gone too far in terms of your pH, so your math can be a little off. All right, so notice there's a difference between equivalence point. Equivalence point is right here where all the ions have balanced each other out. Endpoint is dealing with your color change, your indicator, okay? So if your indicator is a little off to where your pH is, then it could be a little bit different, and your calculations could be a little off. So what does a titration actually look like? Guys, we have this thing called a burette. That's this long volumetric tube right here where we have our known substance, okay? Now it says, you know, a base right here, but it could be the known acid. Big thing that's in the burette is we know the molarity, okay, inside the burette. Down here, this is where we put our unknown, okay, which is in the flask that we're going to receive it. So this formula, guys, is what we're going to use. And this is simplified. This is on table T. You do not have to memorize this. But basically, it's the molarity of our acid A, which we would have to either we're solving for that or we know it. The volume of the acid, which is how much we use. So we're always going to know, well, I don't want to say always. Most of the time, at least in terms of our lab, we're going to know the volumes, and we're going to be solving for one of the molarities, okay? And B is just the molarity of our base, and then volume of our base as well. So this should hopefully look like another formula we've already used. A couple formulas we've already used. We've already used M1V1 equals M2V2 for dilutions. Okay, and then we've also used P1V1 equals P2V2, which is Boyle's law. So mathematically speaking, guys, we've done this already. It's just a new application of a formula that we've already used. So let's dive right in, okay, with our examples here. So what's the concentration of a solution of HI? So you got to ask yourself, is this an acid or a base? If it's neutralized by 0.6 liters of 0.2 moles of KOH. So we're looking for concentration of this. Is this an acid or a base? That's going to be our acid. So molarity of A is what we're looking for. We had a volume of A, which is 0.3 liters. Okay, neutralized by this, and this is our base. KOH is our base. So molarity of B equals 0.2 molar. Volume of B is 0.6 liters. Biggest thing, guys, you got to make sure the volumes are in the same unit. That's the big thing to remember here. So MaVa equals MbVb. All right, so solve for Ma. Well, get this by itself. Ma is going to be my molarity of my base, so 0.2 molar multiplied by 0.6 liters divided by the volume of my acid, which is 0.3 liters. Cross those out. Then we just have to do the math. 0.2 times 0.6 divided by 0.3, you should get a molarity of 0.4 molar. Okay. Now let's think, does this answer make sense? Well, our molarity between our acid and our base, well, the base, guys, was much weaker. So this is a little bit different application way to think about it. The molarity of our base is weaker than our acid. So it should make sense that, hey, it's going to take more base to balance that out because it's not as concentrated. So we need to use more of it to be able to balance out those hydrogen and hydroxide ions. Okay? So if you have a concentrated acid and a weak base, you're going to take more of the weak base to neutralize that. Okay, that's kind of the way to think about it. So if you feel comfortable, since we've done this already, guys, I encourage you to pause the video, try to do the next 2 or 3 problems, and come back and check your answers. All right, next one. So concentration of hydrochloric acid. So I'm looking for the molarity of my acid. 50 mils of this solution. So notice, guys, these go together, and that's of my base. So we haven't been given the volume of my acid yet. But my molarity of my base is 0.250 molar. My volume of my base is 50 milliliters. Okay, keep reading. Are needed to neutralize 20 mils of the HCl. There's my volume. Since my volumes, guys, are already in the same unit, I don't have to convert to liters, even though I'm using molarity. All right, they're going to be canceled out. So Ma, I'm just going to, since it's the same as the last one, Ma equals the molarity of my base, which is 0.250 molar, multiplied by the volume of my base, which is 50 mils. And I'm only going to use 20 mils. So let's think about this before we even go through this. What should the concentration of my molarity be? Well, if I think about this, notice how I only use 20 mils of my acid and 50 mils of my base. So what does that tell us about the molarity? Is it going to be stronger or weaker? it should be stronger. So the molarity that I get here in this problem, guys, should be higher than 0.25. And when I go through and do the math, I end up with 0.625 molar for my concentration of my unknown acid. All right? So that's two problems. You guys definitely try this one on your own and come back for the answer. So, particular acid has a concentration. Oh, notice how we know the acid concentration here. It's 0.1 molar and a volume of 100 mils. What volume of a base with a molarity of this? So we know the molarity. We're looking for volume. How much is going to be needed to actually perform this titration? 0.5 molar. Vb equals question mark. So notice, which substance is my weaker substance? All right. The acid is weaker and my base is stronger. So are we going to need more base or less base than acid? We're going to need less of it. So our final volume, guys, should be less than the volume of our acid since this is stronger. So I need to solve for Vb. Means I'm going to divide by the molarity of my base. Vb equals molarity of my acid is 0.1 molar. Volume of my acid is 100 milliliters. And the molarity of my base is 0.5 molar. Molar is going to cancel out. When I do this math, I should end up with 20 mils of base would be my final answer. Okay? All right, challenge problem. Okay, keep going through it the same way. Notice that I have my molarity of my acid is 1.0 molar. Oops, not the right unit. I have volume of it as well, and that is 50 mils. What volume? So I know the molarity of my base is 0.5 molar, and I'm looking for the volume of my base. But what's different about this problem versus the other ones, guys, that we've done? Okay, this is a diprotic acid. So in their solution, they have twice as many hydrogen ions. Okay, so what does that do to our molarity, really, of our acid? Now, the molarity is still 1.0 of the entire acid. But really what we're doing here, guys, in this titration is like we did, and we did this in our pH calculations where we had to take into account that, hey, when I have a 1 molar solution of acid, how many hydrogen ions do I actually have? I really have twice as many because you have 2 ionizable protons. So we've got to multiply this concentration by 2 to get 2.0 molar. Okay, and that's what we will work with from here. So Vb is what I'm looking for. So it's the molarity of my acid, which is 2.0, multiplied by 50 mils, divided by 0.5 molar. So my final answer I should end up with is 200 mils of my base, because again, this only has sodium hydroxide only produces Na plus OH minus, so there's only one hydroxide, but this guy produces 2 H plus ions plus SO4 2 minus. So hydroxide has to work twice as hard, or we need twice as much to balance out the number of protons. Okay, so these are some practice examples. Go through, do this calculations page. You will have this on your summary quiz. Till next unit, I'll see you later.